The question was, why can we think of these dual variables as prices? So here is maybe a more concrete explanation. So before, I think I just misspoke. These U's correspond, of course, to rows of A, not columns of A, because every row is a particular constraint on a resource. And even the dimensions wouldn't work out if it corresponded to columns. So I just misspoke there. Right? So I'm taking U transpose AX. So U has to line up with the rows of A in terms of its dimensions. So every component Uj I can think of as the price for a particular resource, the resources being along the rows. Why can I think of it that way? Well, I think that comes out of this. So you could interpret it in one way like this. Another way to think about it is just right from the primal dual relationship, stationarity condition, which is this one. It's also the way we get the primal updates in our dual method. So x plus, the next primal update, is given by minimizing f of x over all x plus U transpose AX. That's what we've seen a bunch of times so far. I'm just recalling now that I'm just going to write out this product of a vector with a vector more explicitly. This is the sum of Uj times the jth component of AX. Just writing out the inner product of these two vectors, this one and this one. Okay, so let's just flip the min to a max so we can think about this in terms of the context of that problem a little better. I'm just going to say that x plus is also the argmax of the minus of the negative of all this stuff. It's a totally equivalent statement. I haven't changed anything, right? And I'm going to call minus fg. I'm just going to have a minus here, sum of uj, ax in the jth component. So now I can actually read off directly the interpretations of each of these components. Let's suppose that this I think of as some utility function. So I want to make this as high as possible. It's some utility I derive from my allocation of goods. Okay, so I'm trying to make this as high as possible by allocating goods x accordingly. But I have some resources that I have to use. This is the amount of resource j that I've used across all of my different units, it's ax, in the jth component, because every row of A corresponds to a particular resource. And look, I'm trying to maximize my utility minus some linear combinations of resources. I interpret the weights here as prices. The steeper the price, the less I'm going to want to use of it. It's directly how I can think about it. The smaller uj is, the smaller the price, the more I feel like I can use of it. So forming this inner maximization problem to get our next primal variable x plus, we can interpret kind of directly in this context. Does that help a bit? Yeah? OK. So that was dual decomposition. Why didn't we stop there? Why is there anything left of the lecture? Well, it turns out that if you were to go implement this, then you would find a few things. One, they tend to be pretty slow in practice. And two, actually, you don't have very good convergence properties. And convergence in particular of primal iterates. So yes, we do have, because this is a standard gradient ascent method or subgradient method, we do have convergence of dual variables per our theory we worked out earlier in the semester. Under various conditions, we get different rates, etc. That's what we said here. But nobody told you that these primal variables are also going to converge. Okay, that's something completely different. At optimality, okay, theoretically, if we had the optimal dual variable u and we were to minimize that, it would give us the optimal primal variable x. That was a stationarity condition. But if we have u approaching optimality, it actually requires a fair bit more conditions to prove that x also approaches optimality. So if you go and implement this, you'd see that maybe you converge on the dual. Maybe it was reasonably quickly at the same speed as the first order method, but you did not get primal convergence. So you didn't really solve the problem that you wanted to generically, unless you had more assumptions in the problem. So that's where something called augmented Lagrangians come in. And they are an odd trick when you see them for the first time. And they ensure, pretty much all they do is they ensure that you get convergence under more broad conditions. So they have better convergence properties in terms of primal variables. All you do is instead of minimizing f of x subject to ax equals b, that's maybe the problem you want to solve, you add this term to the criterion, rho over 2 times the L2 norm squared of ax minus b. Of course, given the constraint, that didn't change anything. That is the same problem, right? Because if the constraint is that ax is equal to b, then that term is actually equal to 0 on the feasible set. Right? So I didn't change the problem at all. But what it's done is it's actually kind of smoothed my primal criterion. Smoothed my primal criterion out quite a bit. And let's consider now, let's consider running something like the dual gradient ascent method that we learned, but on this problem, where I've added this term to the primal that doesn't really have any effect. What you'll see is that all that happens is that where I would be minimizing f of x plus u transpose ax, I'm now minimizing f of x plus u transpose ax plus the other part of the primal criterion, rho over 2 ax minus b. Okay, and this minimum was unconstrained for our construction in the dual. So this is actually a different minimization problem, no? And it's a smoother one. In particular, this is always going to be unique, for example, if A has full column rank, because this will always be strictly convex, this function that we're minimizing here. But it generally just smooths out this inner step. And OK, now we should be adding for our dual variables what it was before, plus some step size times ax minus b. And I've actually just called the step size rho. So I'm going to explain that choice in a second. But this you could think of as t. This was just my step size. Okay, where rho is the constant that I decided to multiply the L2 squared term by in the first place in the primal. So let's pause for a second and just observe that this is a different algorithm. Even though I've actually made the primal, I've only done an equivalent transformation to the primal, I've actually changed my algorithm now. So there's good and bad about this. I'll just tell you them right away, and then we'll discuss more about this choice of rho. The good part of augmented Lagrangians is that they converge. They have better convergence properties in terms of the primal iterates than the regular dual methods do. And we're not going to cover the details for that. This is kind of more or less classic literature. And if you read the Boyd paper that I reference at the end of the slides, then you can find some concrete pointers to that. But essentially what this does is that it provides a lot of smoothness to this minimization problem, and that's helpful for convergence in the end. Okay, so they have better convergence properties than dual methods do. What's the bad part? Well, the bad part is that even if f decomposed across blocks of variables, then I can decompose this, but I can't decompose that. They actually kill decomposability. Right? This L2 norm squared is clearly not going to split up across blocks of variables. If I were to have something like, if f was the sum of fi of xi, and I had a constraint like this, which I could rewrite as something like this, then the problem is that last term, which is this. This doesn't decompose. So in fact, we cannot break up. It doesn't isn't decomposable. Okay, so we can't break up that thing across blocks of variables. That's the bad part. So why do we choose the step size to be rho? Let me say that first, because we're going to very quickly move on from augmented Lagrangians to something else called ADMM. But I want to motivate this choice of step size rho first. This choice of step size rho, so it could have been tk at the kth iteration. I'm calling it rho. It was chosen because actually under that choice of step size, we can see that our variables x and u at the kth iteration are going to satisfy the stationarity condition for the original problem. So it's going to be a choice that's motivated by that observation. Why? Well, right, by construction, because xk minimizes f of x plus u transpose ax plus rho over 2 ax minus b squared. That's how we choose xk at the kth step to minimize that quantity. if I were to take the subgradient of this with respect to x, set it equal to 0, and plug in xk, then that should be satisfied. It's just subgradient optimality. So that means that the subgradient of f evaluated at xk plus, it's going to be the gradient of this part with respect to x evaluated at xk, because this part's differentiable, ends up just being A transpose u plus the gradient of this with respect to x, which ends up just being A transpose times rho ax minus b. So all I've done is I've pulled out the A transpose from both terms. Then this just comes directly from the fact that xk was chosen to minimize this criterion. And look at this part. If I happened to just call this my dual update, if that was my new dual variable, uk, which I would have gotten if I had taken the step size to be rho, then I've just shown that the subgradient of f at xk plus A transpose uk contains 0. That is the stationarity condition for my original problem, right? This one, say. Or the one, this one without the extra Lagrangian term, rho over 2 ax minus b squared. So if I've satisfied primal feasibility, and I've satisfied that, then I'm done. Yeah?
But even then, that's not your update, because you're taking ax k minus 1.
That was just a typo. So thank you for pointing that out. So this is supposed to be, right, as soon as we get the x variable, we're supposed to push this into the computation of the subgradient of the gradient for the next step. So this is supposed to be xk is the argmin of blah, 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 and then uk is supposed to be uk minus 1 plus tk times axk minus b. And this we're just going to choose to be rho. So I should have it properly done all the other slides. Wow, is this a typo that's... That's not good. So everywhere on the slides, make sure to fix that right away. Hope you guys weren't confused earlier. This should always be the latest value of x. Otherwise, I mean, the steps just seem a little bit backwards. As soon as I compute the minimum there, I'm using that to get a gradient of my loss function, the dual loss function. So that should be the most recent version of x. Thank you for pointing that out. So I have to do a grep of xk minus 1 with xk after lecture. OK, so we have now two methods. We have dual decomposition, or really dual methods, which decompose in the case that the criterion function in the primal splits up. And we have augmented Lagrangian methods, which don't decompose, but have better convergence properties. And between the two of them, you might want to use one in one situation and one in the other, but we don't really have methods that both decompose and have good convergence. And that's where ADMM comes in. So ADMM is the full name of this method is the alternating direction method of multipliers. And it tries to combine the best of both worlds. It tries to take the good convergence properties of augmented Lagrangians along with decomposability associated with the usual dual methods. Okay, and this is a very old method. It's as old as either of these other two methods. But it wasn't until recently that people in the ML and stats community for optimization started paying attention to it. So it's gotten a lot of popularity in the last 5 years, say. So let's consider the following minimization problem, just for simplicity. Minimize, so I have f splits up over just two blocks of variables. F1 of x1 plus f2 of x2, subject to a constraint ax equals b, which I'm just writing as a1 times x1 plus a2 times x2 equals b. So what does ADMM do? It proceeds in the first step just like augmented Lagrangians do. It adds rho over 2 times the quantity ax minus b and the L2 norm squared to the criterion. Attempts to smooth out the minimizations that we're going to be performing subsequently to get better convergence properties when we do our primal updates. So this is the problem it considers. It's equivalent to our first problem because of the constraints. And now we write the augmented Lagrangian. So we form the Lagrangian just for this problem. Start with this problem, introduce a dual variable for this constraint, form the Lagrangian, It's a function of x1, x2, and our dual variable u. So there it is. It's just exactly as you've practiced a bunch of times when deriving duals. And ADMM repeats the following steps now. Okay, it first does a minimization of this augmented Lagrangian, which is f1 of x1 plus f2 of x2 plus u transpose ax minus b plus that augmented term rho over 2 times the norm of ax minus b squared. It first minimizes that over just x1 with x2 and u fixed at their current values. Then it updates, it plugs that new value of x1 back into the augmented Lagrangian, and it minimizes it over just x2 with the new x1 fixed at its value and u fixed at its current value as well. It's this middle step. And then finally, it makes a dual update. Okay, I just update u to be u plus rho times ax minus b. So how is this different than the usual augmented Lagrangian method? Well, the usual augmented Lagrangian method would have combined these two into one step. The minimization would not have decomposed over x1 and x2. All we're doing is we're minimizing f of x plus u transpose ax minus b plus rho over 2 times ax minus b squared. And that is the middle step of the augmented Lagrangian method, right? That's just this guy right here. Or that's the primal update for the augmented Lagrangian method. And it would perform that over x1 and x2 simultaneously, because it's just looking at it as a dual gradient problem, say, and it doesn't decompose over x1 and x2. So it would have, in this notation, just with having introduced the augmented Lagrangian, which is nothing more than the terms we saw before, it would have performed that jointly over x1 and x2. ADMM says, I don't care if it doesn't decompose. I'm going to decompose it anyways. I'll just do x1 first, then x2 first. So that is the key difference between those two methods. It's kind of like taking augmented Lagrangians and forcing decomposability on the problem, even though, technically speaking, these two together, x1 and x2, no longer form a gradient or a subgradient of my conjugate function. Okay, this one does. This pair does, because it's an actual minimum. These pair don't, because we split up the minimum across two steps. Okay, it is very important that you actually do these steps in sequence. So that's another difference between the decomposability of dual methods in ADMM, is that actually we are not doing these in parallel. We are first doing the x1 step, and look, then we are taking the most recent value of x1 and plugging it into the x2 update. So those, as I've written it, those cannot be done in parallel. Now, in many applications, we can set up ADMM in such a way that actually these two do decompose and can be done in parallel. That's called consensus ADMM. And I may show you an example of that probably next time, just to show you that you can get decomposability. You just have to set it up properly. And as we've written it here, while they decompose, they're not parallelized. OK, let's just talk about convergence guarantees for ADMM. I may do one example, and then we'll have to cover the rest next time. So under pretty modest assumptions on f1 and f2, and for example, they don't require these matrices A1 and A2 to be full column rank, the ADMM iterates satisfy a bunch of properties. First of all, I get feasibility in the limit. I get convergence in the primal objective, which is something I actually did not get with the regular dual gradient method. Remember, the primal properties were kind of unknown. And I get dual convergence. I get convergence of my dual iterates to a dual solution. We don't generically get primal convergence, so xk convergent to x star. But under a few more assumptions, we do. And so I've left out a lot of details about how these compare theoretically to dual methods and augmented Lagrangians. But maybe suffice it to say at a high level, these have properties that are much closer to augmented Lagrangians than generic dual methods. So you have better convergence with ADMM than you would if you did not introduce this extra term here, this kind of augmented term. OK, so you can see this nice monograph written by Steve Boyd and some of his students that I referenced at the end of the slides for proof of all this, and a very nice treatment of ADMM. It's like maybe 100 pages or something. It's a nice long monograph on all the properties of ADMM. How about its convergence rate? And this is quite interesting. this is something that's not known in general. So unlike gradient descent and classical dual methods and so forth, convergence rates for ADMM are not known in general, but this theory is currently being developed. Because it's become such a hot topic in ML and stats, there are papers that have come out 3 years ago, even this year, that offer proofs of convergence rates for ADMM under various situations. And they're becoming more and more general. They're not nearly as general as what we have for first-order methods, but they're not far off. And roughly behaves like a first-order method or a bit faster. That's what you can think of as its convergence properties. So we'll come back to that next time when I talk more about applications. But you can think of it as roughly on par with the first-order method, but perhaps a bit faster in practice. OK. I think I have time just for one example. And so for that example, I'm going to cover a different way to do alternating projections than what we saw when we talked about subgradient method. And next time I'll come back and I'll do the fused lasso and group lasso examples, where you can see that it gives very simple algorithms for both of those problems. It's very, very simple. So ADMM is often one of the easiest things you can apply. That's really one of its main appealing points. So let's go through this example, and then we'll call it quits. So I want to find a point that's in the intersection of two sets C and D. And we saw a way to do this with the subgradient method. You just basically, we actually set up a problem that we minimized with the subgradient method, that the result of applying the subgradient method to that problem was alternating projections. So we project onto C, then onto D, then onto C, then onto D, et cetera. And eventually we settle somewhere in their intersection. ADMM offers a different way of doing this. And it's different than the classical alternating projections method, and it's more efficient. So we're going to write down our problem as now minimize the indicator of x being in C plus the indicator of x being in D. How do you apply ADMM to that? Well, it seems like you can't, because there's no equality constraint. We do the same trick in this problem, and this is very common in ADMM, that we do when we derive duals. We introduce an equality constraint, just to give ourselves something to work with. So I call this indicator function now being evaluated at z rather than x, and I introduce the constraint that x and z must be equal. Haven't changed the problem at all, but now I can apply ADMM. And I write down the augmented Lagrangian. So let's just do that. The augmented Lagrangian now is a function of x, z, and u. And it's the indicator of x being in C plus the indicator of z being in D plus, so here's a trick that I will show you in more detail next time. Turns out I can actually combine u transpose x minus z and the L2 norm of x minus z squared into one term by throwing away variables that don't depend on x and z, since I'm going to be doing the minimization over that with these guys. And that is this. So this is called the scaled form of ADMM. It's often the easiest way to set up problems with it. I take the inequality constraint that I had equal to 0, and I add the dual variable. I take the L2 norm that squared. That is the contribution I would have gotten from both the linear term with u transpose x minus z and the quadratic term on x minus z alone. So that's my augmented Lagrangian. And now I just look at this and I say I have to minimize this over x, then over z, then do a dual update in u. So minimize over x. What are the terms here involving x? It's just this and this. And you can see actually this ends up looking like a projection of what are the terms here that don't involve x. I guess we can write it of z minus u, right? Because I can write this as z minus u minus x squared onto the set C. Because if I'm going to minimize this over x, then I have to make sure that it's in the set C. Otherwise, this is infinite. And to make this as small as possible to stay within the set C, it's just a projection. Minimize over z. It's now a projection of x plus u onto D. And then the dual update ends up just being in this scaled form. So u plus is just u plus x minus c. Usually I'd have a row here, but because I'm using scaled form, there's no row. So we'll cover scaled form in detail next time. But let's just end by saying that this is different than alternating projections, because alternating projections would not have a u, and this would project back and forth between c and d. This one actually includes a dual variable, and it's a lot faster, so you can try it in practice, than the usual alternating projections method, because it uses this kind of additional dual variable to guide the projections. OK, I will see you guys on Tuesday. By that time, we'll have graded the midterms, and I can also say a few comforting words about that on Tuesday. So.